Right, so this is an overview of our test bench setup for the Nissan Leaf motor. This is the motor we plan to put into our MX-5e as part of our OSSEV project. Let's start. As you can see, we don't have any high voltage batteries here to run the motor and the car. What we have is a standard mains plug with a 13 amp fuse. This is going to give us 230 volts AC and a maximum of about 3 kilowatts. This then feeds into this high voltage bridge rectifier here. This one's rated at 1000 volts to give us a high voltage DC output, which goes through our pre-charge and contactor circuit into the inverter terminals here. For our 12 volt system, we're using a spare car battery, which is trickle charged via a Optimate 3 trickle charger. The battery then feeds into our 3D printed housing for our fuses. We've got space for many more fuses because we're planning to rewire the whole car. The main fuses here we have are, the top one is for our driver control unit, which I'll talk a bit more about. Then the second one down is for the Thunderstruck vehicle control unit, the VCU. The third one is for the Nissan Leaf inverter, and the blue fuse is for the Tesla coolant pumps, which we plan to use. Here you can see the pre-charge circuit and the main contactor, which switch power to the inverter inputs. These are controlled by the VCU. So this is the Nissan Leaf motor and the inverter sitting on top. Ours was actually delivered with the charging unit on top of that again, which we've removed, and a whole bunch of cables, most of which we don't use. As it turns out, for our bench testing, we didn't really need to build the cooling system, but we wanted to do it anyway to work out where all the temperature sensors needed to go and to test how well we could control and monitor the Tesla pump that we're using for the cooling system. This is not something we're particularly proud of. We bodged it together with some old silicone hose, and we've got a plastic 5-litre can as our header tank, but it does the job. Here you can see we've got the feed into the inverter, which then comes out of the inverter and into the motor. Back out, it would then go via this temperature sensor into our radiator if we have one, and then we have the pump pumping it around the system. Of all the cables that were supplied with our motor, there's only one you need, and you can see here that we've stripped it right back to just the wires that we require. The cable is the one that plugs into the inverter here, and it basically runs down with some shielded cables to this connector here. This thing is the motor resolver. It's the ICE equivalent of a camshaft position sensor, if you like. Basically is providing feedback to the inverter so it knows what's going on with the motor. There's actually a temperature sensor hidden inside there as well. And if you look around the back, this also connects to a coolant temperature sensor. This is the Thunderstruck VCU. This is basically talking to the inverter and doing the control between the FNR switch, forward, neutral and reverse, and the throttle to actually make the motor move. You'll also notice that there's a blue and green lead coming out, which runs up to the inverter. This is the CAN bus. This is our driver control unit, or DCU, that we've been developing. This is based around some open source hardware. In this case, we're using an Arduino processor and a bunch of PCBs to provide I/O capability. This will provide security for the car. It does data logging. It has GPS module. We have a 3-axis accelerometer with compass. We have audio capability, so it can play audio files and provide audible feedback when you press buttons, for example. The DCU will actually interface some of the controls on the car. So here we have a control box for the driving mode, with green being eco mode, blue being normal, orange being sport, and red being race mode. In the next video, I'm going to show the Nissan Leaf motor running in forward and reverse.